So let's get back to homodyne detection. So omega if is equal to 0. So I of t is equal to, again I am just saying it is root of Ps root PLO cos of delta phi. And I can always adjust my cos of delta phi to be such that delta phi is equal to 0. Assuming I can do that, then my I of t is equal to 2 root, sorry I missed a RD, right? There is an RD here. And of course, this PS is having your modulation. So, what is my, this is what matters as far as the power is concerned, average value of signal power, right. Signal power is proportional to square of the, the current, average current. So, this is going to be 4 times Ps, because I average this, I have to average the signal also, PLO RD square. I will just say proportional to, because every time I can't, I am just saying it is proportional to, because there could be other constants which are DC conversion factors and so on. For direct detection receiver, what is my signal power? The numerator was RD square Pin square, or Pin was PS, average PS square. So, what is the improvement? Improvement in signal power, sorry, 4 times PS PLO RD square divided by RD square PS square. So, the improvement is 4 times PLO divided by PS. So, I get much larger power at the signal power at the receiver, and larger is my local oscillator power, more is my signal power. Okay, typically what is the magnitude of the PLO? So, typically people use, so how do I decide the magnitude of PLO? What was the purpose of putting that PLO in the system? To operate in the short noise. So, if you ask me the question, what is the magnitude? The magnitude should correspond to this power. I should go above, much above this power at which my short noise is equal to thermal noise, to push my system into the short noise dominated regime. And for practical systems, it comes out to be about 16 or 17 dBm of power. 16 dBm, 10 dBm is 10 milliwatt, 13 dBm is 20 milliwatt, 16 dBm is 40 milliwatt. You typically use something like 30 to 40 milliwatts of power to push this to thermal noise, to short noise limited system. Now, if we do the same thing for heterodyne detection, what is different in heterodyne detection? Everything is the same except that there is an omega if. So, if I take the average current or average power, I have to average this, I have to average this, I have to average this, that sense, and I have to average this also. In fact, not average cos of omega if. So let us just write it first. Your I of t is equal to 2 root all right. Now for heterodyne detection, omega if not equal to 0. So essentially I can visualize that there is a IF frequency over which my signal is appearing as a modulation. This is my data which is appearing as a modulation over my IF frequency. So if I take the average current to calculate SNR, by the way, you have to always remember one thing: when you calculate SNR, you always say signal power divided by noise power. Noise power, there is no problem because that's noise variance is all defined. In signal power, do you take the peak power of the signal or average power of the signal? Because the peak power is the power when you have a high state. Average power, null power is when you have 0 state. So which power will you take? Or do you take an average power? So you have to define what power you are taking. So you have to say SNR average will correspond to average power of the signal. SNR peak would correspond to the peak power of the signal. And they could be off by a factor of half because you are using NRZ with 50% chance of probability of 1 and 50% of chance of 0. So peak power and average power will differ by a factor of half. Peak power will be twice the average power. Okay. So that's a very small subtlety there. So I'm continuously taking average power here. So this would be equal to, or this would be proportional to 4 times average signal power times PLO, and average of cos square. Doesn't matter what your modulation is, it's just a cos square function. What is the average of cos square? Half, right? So this would be half. So this is equal to 2 PS PLO. Of course, there is an RD. So improvement in signal power is and you are trying to compare with direct detection like what we did earlier. Earlier we got 4 PS PLO RD square. Now you will get, of course there is RD square because you are taking a power, right. So here you will have 2 PS PLO RD square. So earlier we got a benefit of 4 PLO divided by PS. Here it is going to be only. So this is the trade-off. If you are doing all the hard work to get to homodyne detection, your improvement is improvement in signal power. Remember, this is not improvement in SNR, okay? This is just improvement in the signal power. How much power is essentially reaching the receiver, right? Signal power, electrical power reach that comes out of the receiver. That is double when you are doing homodyne, and it is 3 dB down. The benefit that you got because of this coherent detection is 3 dB lesser for heterodyne detection rather than homodyne detection. But what is the advantage of the heterodyne detection? I do not have to worry about locking my local oscillator with that of the signal and so on. See, another subtlety in locking is that, you know, I very easily said that delta phi should be maintained as 0. What is this delta phi? Delta phi is phi s minus phi LO. That should be maintained as 0, which means you need to have a phase locked loop which locks the phase of your, not just the frequency but also the phase of oscillation of your local oscillator and your incoming signal, right. That is a difficult process, but if you can do that, you're getting a 3 dB benefit in terms of the sensitivity, in terms of the power that I'm able to get. But otherwise in heterodyne, you're getting an improvement in signal power this way. But the real test is what happens to SNR. Do I get a benefit in SNR? Okay. So let's calculate the SNR of heterodyne detection. The question is, will that be anyway dependent on omega IF? Will what be anyway dependent on IF?
Current or SNR. SNR is average. So
We have still not calculated SNR. So we will comment on SNR after we calculate SNR. But this I average is not going to be dependent on my omega IF, because it's just an average of a cos square function. Right? Now there are small things like, what would your IF be? Should it be outside the bandwidth of the signal, inside the bandwidth of the signal, and certain things you may want to consider, because you may not want to interfere with your signal bandwidth. So you'll try to keep your omega IF outside the signal bandwidth and so on. Right? But this is a real test. What is your intuition? Would the SNR improve, or is the SNR degrade, or the SNR remain the same in comparison with so two comparison we need to make. One is with the Homodyne detector and the other one is with a direct detection receiver. So I would so take a guess. Would my SNR improve in a Homodyne or a Heterodyne receiver? You think it is going to improve? Let's see whether it is going to improve. Let's quantify the improvement. So how do you quantify SNR? You will say signal power divided by noise power, and let's stick to average signal power. So SNR average, let's stick to SNR average. So SNR average, I am specifically saying this average because everywhere we have taken the average current, okay, is equal to, what is the average signal power for heterodyne? Which is my signal in heterodyne? This is my signal in heterodyne. And what is the average signal power? This is my average signal power, right? Twice PS PLO RD square divided by, what do I take as noise power now? Should I do short noise? Should I do thermal noise? Should I do both? I just do short noise because that's the whole idea, right? I mean, I wanted to push it to only short noise limited system. So I just have to worry about short noise. And what's a short noise? Twice Q RD. This is my 2 ES ELO was my intensity. So what should be the corresponding short noise? What should I write? I know that sigma S square is equal to twice Q RD times PS. So 2Q RD PS was my short noise, but instead of PS, what is the dominant power that's falling on the receiver? It's PLO. So all what I need to do is I have to just write it as 2Q RD times PLO, of course multiplied by the bandwidth. Bandwidth we were using the notation delta F, right? So let's look at delta F. So this times the bandwidth. Because short noise is dependent on the optical power falling on the receiver, the optical power is predominantly, ideally I should write PLO plus PS, but PS is very small when compared to PLO, so I will just write it as PLO. And so this is what? Your PLO, of course there was no average PLO, it is just PLO, okay. So PLO got cancelled, so what you have is PS times RD divided by Q times, instead of bandwidth I will put delta F. I can write RD in terms of quantum efficiency. You had a relation connecting RD and quantum efficiency. remember RD is eta times Q divided by h nu. So, if I use that, this is going to be eta times Q gets cancelled, Ps divided by h nu times delta f. So, did you get a benefit when compared to a direct detection receiver? How would you have calculated this for a direct detection receiver? SNR for a direct detection receiver in the short noise limited, we have calculated that, right? In the short noise limited condition, SNR for a direct detection receiver, we derive that. That is the reason actually we it is eta times number of photons, but in terms of it is eta times, this is the relation we have, eta Pn divided by 2 h nu delta f. Here you got eta Pn is the same as Ps in our current notation, right? This is the same as Ps. So, it is eta Ps divided by h nu delta f. So, you did get an SNR benefit. You did get an SNR benefit, but the point to notice is that SNR benefit is not a function of PLO. It is just a constant 3 dB improvement you got. Now, what would be, so when compared to direct detection, so this is direct detection, this is heterodyne. Heterodyne we just derived in the previous page, which is SNR is equal to eta Pin or eta Ps divided by h nu delta f. Now, homodyne SNR will be, we just calculated the signal power is a factor twice, right, because we just said between homodyne and heterodyne, the signal power was half when compared to the homodyne. Noise power remains the same. So, what should I get? I should get 2 eta Ps divided by h nu delta f. So, clearly there is an SNR change. I can say that with respect to direct detection receiver, if I do homodyne, I get 4 times improvement, 6 dB benefit in SNR. 6 dB in SNR is a lot of SNR. When you try to talk about systems where you are trying to optimize or minimize the received power, you always want to operate at minimal received power. Minimal received power and the best SNR, that's the ideal condition. Why minimal received power? So that the link length can be as large as possible, you can allow a lot of attenuation, but the best SNR, and that is given by homodyne. That is the best way to do it. But because of the practical issues with the homodyne, we may move to heterodyne, that is still giving you a benefit of 3 dB. But the interesting thing to notice, whether it is homodyne or heterodyne, it is independent of, the improvement is independent of PLO, provided the PLO is larger than the power, or rather I would say that it is, the operation is such that it is in the short noise limited condition. PLO, this is much larger than the power for which sigma t is equal to sigma s square. Once you are able to increase your LO power, you do not have to keep increasing your LO power to 50 milliwatt and 60 milliwatt and 70 milliwatt and so on. The moment you cross the power for which sigma t is equal to sigma s, you are already in the short noise limited condition, and once that happens, your improvement, you will get definitely a 3 dB benefit. That is not dependent on my LO power. Okay. So, do not think that the LO, as you increase, the other thing is, as your LO power increases, the short noise increases, so my SNR is going to degrade. No, it is all getting cancelled in the numerator.